Thank you for the introduction and welcome everyone to this last talk of the session titled Ultra Miniaturized Absolute Rotary Encoder Integrated into a Hinge Joint. Some of you maybe wonder how such a title is connected to the biomedical field. And the reason is that this work is part of a bigger project called Miracle that, as the name stands, means minimally invasive, robot-assisted, computer-guided laser osteotomy. And the idea is to develop a robotic endoscope able to perform bone cutting using laser. To be successful in such procedure, it's really important that we are able to position the endoscopic tip accordingly to the surgical preoperative planning. And here is where we face our first challenge, since such an endoscope cannot use a standard navigation system like optical tracking due to the no line of sight caused by the minimally invasive procedure, and also electromagnetic system cannot be used due to the magnetic interference caused by the robot itself. So for this reason, by looking how the system is designed, and we have like several links connected to each other thanks to rotational joint, one possible way to reconstruct the end effector position would be to position a rotary encoder in each one of the joints. And by measuring the angular rotation of each one of them, we can then use the forward kinematics to reconstruct the shape of such a system and also the end effector position within the body. So now it's important to also list all the characteristics that such an encoder needs to have. It needs to have a very small footprint since, as you can see on the right side, we have the cross-section view of the endoscope, and the external diameter of such a system is 8 millimeter, and we cannot place our sensor over this diameter. And at the same time, we can also not use the internal channel that is 4.8 millimeter because it's dedicated to all the surgical instruments that need to arrive on site. At the same time, we want our sensor to be an absolute encoder for safety reasons. It needs to have a measurement range of plus minus 30 degrees, and calculating also the back propagation error among the multiple links, we estimate that our system needs to have a plus minus 0.05 degree as a max measurement error. So we looked a bit around and we couldn't find any commercial system that would fulfill such characteristics. And that's the reason why a couple of years ago, we developed a novel angular measuring principle that we also patent that is called ASTRAS, the stand for Angular Sensor for Tracking System. And it works as follows. It's based on two main parts. We have like a fixed part that is called stator, where we have active elements such as an image sensor, an LED, and a shadow mask that is used to block the light except for the central part. And here we also have a front view of the stator to better explain where the LED is located, is below the image sensor, and we have like an element, a light blocker, to avoid the light of the LED to enter directly into the image sensor. On the other side, we have a moving part that we call the Rauter, and it's basically a mirror that it's constrained to have just one rotational degree of freedom. This is very important. And such rotational degree of freedom is represented by beta. Here we have like two possible position orientation of such a mirror to explain how the system works. We have our LED that is turned on, and the light is projected towards the mirror. The light is then reflected back into the sensor, passing through the shadow mask. This creates a unique shadow that depends on the orientation of beta, or the rotation of beta. And by measuring like the displacement of such a shadow corresponding to the reference one when beta is equal to 0, we can obtain what here it's called a shift. And also by knowing the distance between our shadow mask and the image sensor, we can then reconstruct the rotation beta. This is an absolute encoder, and shown as such, it has a theoretical range limited to plus minus 90 degrees. So now that we have a concept, we look how to miniaturize such a sensor. And the idea is to use a flexible PCB that would be also our cable to transfer all the data from the camera. And on the tip of the system, we install like an eye 2D camera that is a CMOS sensor with a size of 1 by 1 by 0.5 millimeter. And on top of that, we put the shadow mask that has a 60 micron slit in the middle. We glue it on the top. We have the LED placed below the image sensor, and we have the light blocker shown before. So once that the active part of the system is done, we now focus on how the endoscope joint is done. And here we have some images, a CAD one, and also a real image. And as you can see, the hinge joint are the following. And the idea is that we need to modify such a joint in order to fit our system. And from the stator, we had to mill out a small part of metal in order to fit the NI sensor. And on the other part, where we have the round joint, what we call rotor, we flatten out the surface to create a mirror. And here you can see how we assemble all the system, where we have the image sensor, the shadow mask LED on the stator side, and we have the mirror that is the rotor part. And here there is a video that can show better how we integrate the system. Here we have now an exploded view with all the different components. So here we have the stator. We have our flexible PCB with on top soldered the NI camera, the LED. On top of the camera, we have the shadow mask glue, and we have the light blocker. On the other side, the rotor side, we have our mirror that rotates around the center of rotation. And here we have another view, a top view that shows how the system works when we rotate. So now that we built our system, we wanted to acquire some data. So we create our calibration setup. We connected our hinge joint to an optical table. We fixed one of the two parts of the joint to it, and the other was free to move, but we connect to that like several optical trackers to have like a ground truth rotation. Then we start to move our system in at different angle beta, and we start to acquire also images thanks to the acquisition board. And then once we collected a lot of data, we were synchronizing them. So for each image, we have also the ground truth angle given by the policies tracking system that we used. And the next task is how can we map the image to the proper angle. To do so, I first want to also show you which kind of images we were acquiring. So for the angle 0, we had such an image. And by rotating the system at different angles, we can see that the light stripe that we had at the center moves to the left or to the right side. So what we can see here is that the main information to reconstruct the rotation is along the x-axis. That's why, to simplify also our processing, what we do, we average our image along the epsilon axis. This helps also with the noise reduction. And then we tested like 3 different algorithms to find the peak position with sub-pixel accuracy. We use first correlation, and then we interpolated the correlation curve. We use like the Gaussian fitting, and also centroid algorithm. The first one gives us like the relative position between the reference image and the one that we have, while the other two gives us the absolute peak position along the x-axis of the CMOS sensor. And now with this information and the corresponding angle for every peak position, we could generate our calibration curve using a polynomial fitting. Here are the results. So we took other data set, independent one, and we tested the performance. So the systematic error that we obtained using the calibration curve generated before are the following. We can see that the 3 different algorithms perform more or less the same. The centroid is slightly worse, but they are more or less within the range of error of plus minus 0.2 degree. We also test like what is the precision of the system. We look at a specific angle, and we took like thousands of measurements, and then we plot it, and we see that the sigma for our precision is the following. Here the centroid algorithm performs a bit better. And since you can notice that all the distribution are normal, we can also define the resolution of our system as 6 times the precision, or 6 times the sigma. And considering that our measurement range is plus minus 22.5 degree, this means that our system has a 12-bit or 13-bit resolution. With this, I would like to conclude. The system that we developed has a really small footprint of 2 by 1.5 by 1 millimeter. This considering also the distance between the camera and the mirror. The systematic error is limited to plus minus 0.2 degree. the resolution is 12 or 13 bit, and the measurement range, as said, is plus minus 22.5 degree. For future work, what we would like to do is to even reduce the footprint of the system, since there are commercially available cameras that are even smaller than the one that we use, and maybe design an ASIC in collaboration with some industry. We want also to improve the performance of the system by using a more accurate calibration standard and improve also the processing. And furthermore, we want also to extend the measurement range in order to meet the requirement for the Miracle project previously presented. And with this, I would like to thank you for your attention.